And in fact, that's the lunation, the period, relative to the stars, if the Earth was stationary relative to the Sun. But of course, it's not stationary, it is moving around the orbit. And so here you can see that if it starts off here, and then 1 month later, as it's not there, it's moved over a little bit. So you can see that the sidereal time, the time it takes the moon to spin on its axis once, at the sidereal, it would be pointing here away from the Sun, and so the moon, if you like, won't be aligned with the Sun. So you have to actually let it go a few more days for it to swing over so that it is aligned. So that, and we call that the synodic month. So it ends up being about just over 29 and a half days, or 29 days, 12 hours, 44 minutes and 2.8 seconds. Can you follow that? Yeah. Okay. And that day, as you can see, is suspiciously close to the month, the length of a month, and in fact that's where the origin of the word month comes from, because there's one lunation of the phases, or in German, one Monaten or 1 month. So the original calendar was based, lunar calendars were based on the synodic month, because that's what they were seeing. They weren't looking at the sidereal rate, they didn't know what that meant. They were looking at the synodic month, that is the time it took to go around to complete its phases. It's not quite, this is the average, because depending on where the Earth is in its orbit, if it's a little closer, because it's an elliptical orbit, if it's a little closer, it actually moves faster, and so it's moved over a bit more, so it has to, the moon has to swing around a bit more for it to be aligned. And likewise, when it's further away, it moves a little bit slower, so it lags a little bit. It may only make it here, so it doesn't have to move around a little, as much to get there. So this is the average of the lunations. And many civilizations or cultures in the past were based on the lunar calendar, because it was easy, as I said. You didn't have to make any measurements or anything. You just look up and you can see it. And one of those, which will be critical for our purposes, for our discussion today, was the Hebrew calendar. It was a lunar calendar, and it had 12 months of varying lengths, as you can see, so that the total came to 355 days roughly. Some of these had different dates because, according to Jewish tradition, some dates couldn't occur on certain days, so they made up for it by adding an extra month or taking it off. And so it could be 353 days for its cycle, or for its year, or 355. The first month of the Jewish calendar was Nisan, and it went all the way. Okay. And it was based on what's called the Metonic cycle, and that was so that it could bring bring it all into sync with the seasons. And because of that, it's called a lunisolar calendar, because they wanted to connect the phases of the moon, the lunation, with the position of the sun and the timing of the seasons. The Metonic cycle was actually discovered by a Greek astronomer called Meeeting of Athens, named after him, and he found that that every 19 years you could fit almost a full number of months of lunations in there, 235. So that after 19 years the cycle would repeat itself. So you only had to think about that 19-year cycle. So in this case, the solar year exceeds the lunar year by 11 days. When the excess accumulated is about 30 days, this is in the Jewish calendar, an extra intercalary month was added. So we go from 12 months to 13 months, and this repeats after 19 years. So you had 12 years of normal years and 7 years that were leap years, where you had the extra month. And that was in order to keep the Passover so it continues to occur at spring in the northern hemisphere. Okay. It's one of the rules they have. In addition to the Judaic calendar, there's also the Islamic calendar, which is a lunar calendar also. And they also have these intercalaring months and years and so on, so to keep it fixed with the solar year so that the seasons remain roughly aligned. But for our purposes, our calendar is based on the original Judaic calendar. So that's why I mentioned it here. So Passover in the Hebrew tradition commences on the 14th day of the Hebrew month of Nisan. So that's the date you have to remember, because that has significance for the Christian calendar. Okay, but there are different types of years. I'm going to discuss two. The first one is what's called the sidereal year. Okay. That's the time it takes the Earth to orbit the Sun once with respect to the fixed stars. Okay. And that equals 365.256362004 days. Or 365 days, 6 hours, 9 minutes and 9.76 seconds. Okay. All right. And then there's what we call the tropical year. That is the time the Sun takes to return to the same position in the cycle of the seasons as seen from the Earth. We also refer to this as the solar year. It's the one that we all use. And the reason we use it is because we want to make sure that the seasons are always occur at the same time. Okay? So that's the one that everyone uses. The sidereal year is an astronomical thing because we have to measure it relative to the stars, but the tropical year is the one that we all use for civil purposes. And it equals 365.24219 days, or that in hours, in minutes and seconds, which means that it's 2 minutes, 20 minutes and 24.55 seconds less than the sidereal year. And that's, yeah. And the reason it is because of the precession of the equinoxes. Because you would think, at first I used to think, why isn't it the same as the sidereal year? Because after all, yeah, the seasons are due to the Earth's the tilt of its axis relative to its orbit. And so why shouldn't it be the same each time it comes back? It should be the same as the sidereal year. However, it's because of the precession of the equinoxes, and by that we mean the Earth, you can think of it as like a spinning top or a gyroscope. It doesn't just spin, it precesses or wobbles, so that its axis doesn't remain fixed like this as it's orbiting. Over time, it sort of does a little wobble like that. And that's key. This one's going pretty rapidly. The Earth goes a lot more slower than that. It was actually discovered by a Greek astronomer, Hipparchus, who lived in Nicaea in Asia Minor, and he's considered to be the greatest astronomer of antiquity. A few months ago, when Les gave his talk about the constellations, he showed this picture here with the constellations on the shoulders of Atlas there, and he was the one who came up with that star catalogue of the constellations. He also measured the distance to the moon, did many other things, but he was absolutely brilliant. But he discovered, well, he had access to hundreds of years of records from the Babylonian and the Egyptian civilization. And he spent some time looking through it and discovered that some of the stars didn't appear to be in the same position as they were in hundreds of thousands of years earlier. And he realised that meant that the whole sky, the constellations, the zodiac, were precessing, that is, they were moving across the sky. And he discovered that in 127 BC. And so, to understand that, if that's the Earth in its orbit, right now, that's the direction that the pole faces, the North Pole, points to the star Polaris. But in about 14,000 years' time, it would have precessed and now it's pointing the other way. Okay? you can see here, if this is the position here, it'll be somewhere in the northern hemisphere, but 14,000 years from now, it'll be somewhere in the southern hemisphere, because it would have tipped over the other way. Okay, and so the time it takes to do that that's the sidereal year there, and that's equivalent to 20 minutes. If you go, where was that other one? That 20 minutes. So if you divide that by that, you end up with 25,771 years. In other words, it'll take the Earth that long to do the little precession. So the entire star, the constellation of the zodiac, would appear to move across the sky and then return to where they were and repeat itself. So the seasons will move through the year. That is, in 12,000 years' time, summer in the southern hemisphere will be in June and winter will be in December. Okay. And then it'll be back again. So this has the effect of moving the vernal equinox across the ecliptic. That is the point on the sky that the sun appears to move from the southern hemisphere to the northern hemisphere. Okay. And that is the time of the vernal equinox arrives each year 20 minutes and 24.5 seconds earlier. Okay. And because of that, you have to subtract it from the sidereal year to get the tropical year. Can you follow that? Okay. So here you have it. It's this is the current configuration of the seasons. Okay. When it's tipped in that direction, it's north in the summer in the north, winter in the south, vice versa here, and over here on the equinoxes, it's directly over the equator, hence the name, where you have equal day and light and equal heat in both hemispheres, so you have autumn and spring. If you could plot the position of the sun, because of this, if you could plot it up on the sky relative to the Earth, the sun will appear to move across the sky. Okay, so I've oriented this so that's north at the top and south at the bottom here. For us, it's usually the other way around, but anyway. So here you have, if that's your starting point, and you can plot the position of the sun, it starts off here on what we call the vernal equinox, the spring equinox, and it starts to move north. It reaches the tropic here, and it comes down. You have another equinox here, over here to the solstice of the other tropic, and there. Okay. However, if the Earth was stationary, then the sun would just come back and just repeat itself. That just wraps around. But because the solar year is at 20 or so minutes shorter than the sidereal year, by the time it gets here, it's moved over a little bit, so it arrives that little bit sooner. Can you follow? Okay, and so that's why you the tropical year is there. One interesting thing here is 2,000 years ago, the vernal equinox was in the constellation of Aries. Okay, so that point was called the first point of Aries on the sky, we're at that point. But it's now been 2,000 years since then, and so it's moved over an entire constellation so that now it's in Pisces. We still call it the first point of Aries though. Okay. Likewise over here, and the other thing too is this tropic, we call that the tropic because in Greek the word tropic means to turn, because that's when the sun on its movement across the sky turns and starts coming back down. And when it gets here, it turns and starts moving back up. Okay, so the word tropic. And in those days, in the past, remember everything's moved over this way in 2,000 years, but 2,000 years ago that tropic was in Cancer. So that was called the Tropic of Cancer. Likewise over here, it was in Capricorn, so it was called the Tropic of Capricorn. But now it should be more accurately called, the Tropic of Gemini and the Tropic of, what's that, Sagittarius or something, okay? But the names have stuck. Okay. And again, this one here just shows you the constellations all with the modern boundaries, and you can see it went from Aries to Pisces, and from Capricorn to now Sagittarius, boundary of Sagittarius. This is in Sagittarius. Okay. So that was all to explain what the difference between a sidereal year and a tropical year, and why we need the tropical year, which is the year that we measure, that we use. Jump forward a bit and we come to the Roman calendar. Rome was founded by the brothers Romulus and Remus, who were, according to legend, were suckered by a she-wolf. So this is Romulus and Remus here. So legend has it that they ended up founding the city of Rome, and on the 21st of April, 753 BC, according to our calendar. But for the Romans, that was the year 1. That's the year that they marked their calendar from. So all years in the Roman period were marked from, or measured from that founding of Rome. And they had originally only 10 months in their calendar. The first month was March. Okay, it was the month of Mars. And then the second one was month of April, or Aphrodite. April was the Latin for Aphrodite at that time. Maius, month of Maius. Juno, and then after that they just named them after the number of the month. So it was, they had Quintilis, Sextilis, September, October, November, December, which is why these here coincide. The 7th is the September, October is the 8th, and so on. However, that was the early calendar of Romulus, very early on, but by the time of the Roman Republic, got a bit more sophisticated, and they added 3 new months in there to make it fit in with the solar year. So they had the month of Janus, month of February, and a month of wages when they got paid, and so on. And then they, and this one here was a bit of a weird one because I think that was eventually dropped. And then they had month of Mars and all the way down. So that, yeah, and so things stayed that way, except, oh, and before I get to it, the Roman calendar, they had 3 key days in the month, in their months. The first of the month was always called the calends. The 7th day of the month was called the nones. And the 15th day was called the Ides. For many people familiar with Shakespeare, Julius Caesar, the Ides of March. So an example, the 1st of January was the calends of January. Okay, and then the 2nd of June would have been the 4th day before the nones of June. 10th of March would have been the 4th day before the Ides of March. And 20th of May was the 13th day before the calends of June, and so on. It's a weird way of doing it. However, the Romans, they weren't really interested in that. They were interested in conquering and administering things. Eventually, after many, it gets very complicated, so I won't go into it, but by 46 BC, the calendar had become hopelessly corrupted because various officials and consuls and so on, consuls were usually elected for a period of a year. So it occurred to some of the early consuls that if they just did away with several months or years or added some more, they could stay in power longer before their year was up. They just redefined the year. And things very quickly over a few centuries became hopelessly corrupted. And the calendar made no sense. You basically needed the equivalent of a PhD to know what day of the year it was. It was ridiculous. And so it became so hopelessly corrupted that Julius Caesar was when he became dictator of Rome, decided that one of the first things he was going to do was to reform the calendar. And so he'd recently conquered Egypt and became very close to its queen, Cleopatra. Very close. Yeah. And the astronomer to the court of Cleopatra was an astronomer by the name of Sarkissian of Alexandria. And he convinced Julius Caesar to reform the calendar based on the Egyptian solar calendar, which had 365 and a quarter days in its year. And so they did that, and to show just how hopelessly out of whack everything was, the calendar by then was 90 days out of sync with where it should have been. So they inserted 3 intercalary months, 3 months, were added to the year 46 BC, so that the vernal equinox was put back to around March 25th, which is what it was in the Roman calendar. Thereafter, every 4 years, an extra intercalary day was inserted in February, which is what we have. So we call that the Julian calendar. And for hundreds of years, with the Roman Empire, and then later under the Christian Holy Roman Empire and so on, after the fall of the Roman Empire, it became the calendar of general use, the Julian calendar. The problem was that the length of the year is not exactly 365 and a quarter. It's a little bit less. And so because of the difference in the lengths between the Julian and tropical years, the seasons began to drift. Okay? So that you can see here that that's the length of the Julian calendar, the Julian year, and this is the length of the tropical year. So you end up with that much of a difference in days, which is equal to 11 hours and 14.78 seconds, which equates to 0.187439 hours. Okay, and so how many 11 minutes and 14.78 seconds will fit into a day? Well, it ends up being about 128. So that means that after 128 years, you're 1 day out. Okay, you have an error of 1 day. Now that doesn't seem like much for in our own human lifetime. However, over centuries and millennia, that really starts to add up. And so, but as I said, just keep that in mind. The drift occurs every 101 day for every 128 years. Now, once the Roman Empire became Christian with the ascension of Constantine the Great, in the year 325 AD, he convened the Council of Nicaea to resolve various doctrinal issues and, importantly, to fix the date of Easter, because Easter was considered to be the most important day in the Christian calendar. Now, in those days, the early church was dependent on Judaism to determine the date of Easter, because they had to go and ask the local synagogue, when is Passover? Because they had this weird calendar that no one else understood, okay, and they kept to themselves. So they would go and they'd say, oh, well, it's going to be this or that. Okay, then that's when we start dating Easter. So Constantine and the church wanted to break away from that and be more independent. Okay, so what they did was they came up with a series of rules to determine it independent of the Hebrew calendar. So by 325 AD, the dates had drifted by 2.89 days, just under 3 days. Okay, so the council fixed the date. They said from now on, the vernal equinox will be on the 21st of March, regardless of where you are in the world. Okay, that's it. The vernal equinox, according to our rules, is the 21st of March. Then they use what's called a model moon. That is, not the real moon, the one you see in the sky, but a model moon that would determine the date of Easter. And this moon is referred to as the Paschal full moon. Okay, that is, it's based on that 19-year Metonic cycle, which repeats itself every 19 years. Because Easter is the most important movable feast in Christianity. Movable feast is a feast where different date every year, whereas Christmas and other things are fixed dates. They're not movable. So the rule became, that Easter falls on the first Sunday after the full moon date, based on mathematical calculations, that falls on or after March the 21st. If the full moon is on a Sunday, however, Easter is celebrated on the following Sunday. Okay. So in other words, the way I put it is, it's the first Sunday after the first full moon after the vernal equinox, which is taken to be March 21. Okay. And if you go out, and most of the time, and the thing to remember, I should say, is that this is the although Easter is liturgically related to the beginning of spring in the northern hemisphere, that is, the March or vernal equinox, and the full moon, its date is not based on the actual astronomical date of either event. Okay, it's a model moon. It's a little mathematical model. Okay, and what that means is, for example, let's say the full moon here in Australia happens to fall at a minute past midnight on a particular day. In Europe or some other time zone, it'll be the previous day, which will throw out all your calculations. Okay, because hang on, they'll be a month out then. Because they have to wait another month for their full moon to arrive. Can you follow? So there has to be a model moon, I call it, a mathematical one that's independent of any time zone. Okay, and that's why they do. And the reason they went through this trouble is because Easter is the most important day of the year in the Christian calendar, and they wanted to make sure that was right. So both dates may occasionally coincide with the dates of the astronomical events in some years, but not always. Okay. I think this year they do, but I remember a few years ago they did it, and really confused me. But remember, it's based on that model moon that they came up with, based on the metonic cycle, the 90-year lumination. And that worked fine. From 325 AD, it worked fine. However, by 1582 AD, the calendar dates were now, well, that's the number of years, 1582 to that should be 325. Anyway, you end up with, and divide by 120, end up 9.8 days. So by 1582, you were almost 10 days out, which would have meant that people were celebrating Easter on the wrong day, which could have condemned their souls to hell if they, and that's what they believed. They didn't want that, okay? And so something had to be done, okay? Because the date of Easter started to really diverge. And of course with Easter, that could result in even greater errors, because you might be so much just one day out, but you'd have to wait for the next full moon, so you could be more than a month out, okay? Not just 10 days, but quite a lot. So, since Easter was the most important feast in the Christian church, this became intolerable and something had to be done to fix it. Okay? So, in 1545, the Council of Trent authorised the then Pope Paul III, to reform the calendar. So he started to get all the most brilliant astronomers he knew together to start thinking of it. But the Council of Trent put certain limitations, and they said it required that the date of the vernal equinox be restored to what it was in 325 AD by the Council of Nicaea. That is, they had to put it back to the 21st of March. And to design the calendar to prevent any future drift. Because they didn't want it to then, they didn't want to reform that and then produce another drift. They wanted it to be as stable as possible. So, one of the astronomers that got to work was this gentleman. He was a Jesuit mathematician and astronomer, Christopher Clavius. And in fact, he was arguably the greatest astronomer at the time. He was absolutely brilliant. This guy's brain was incredible. And so by 1582, okay, he had devised a system that had agreement by everyone and ready to go. And his solution was, to remove 10 days. Just take 10 days off the calendar to revert the equinox to the 21st of March. Then impose a leap day in only 97 years in every 400, rather than one in every 4. That is, century years are not leap years, except if they are divisible by 400. So, for example, 1600 is a leap year, it's divisible by 400, but 1700 isn't. So there's no leap year there. Okay? So this ended up making the year, over a long time, 365.2425 days in length, which is very, very close to the tropical year of 365.24219 days. Okay? And so the Gregorian year, in other words, is 365.97 over 400. remember, in those days they didn't have decimal numbers, so they had to always think in fractions. So that's how he was thinking. And he did such a great job that he had the biggest crater on the near side of the moon named after him, called Clavius. It's at the south pole of the moon, on the near side, and if you look really carefully, you might see the space state, the moon base in 2001: A Space Odyssey there somewhere. Okay, but that's how highly he was regarded. So, in October 1582, Pope Gregory XIII instituted the calendar by decree. Now you have to realise that at that time, only the Pope had the sufficient authority and clout to just remove 10 days and have everyone agree to it. Okay? No one else could have done it. The King of England couldn't have done it. No one else could do it. But the Pope had sufficient authority to do it. And so, on the Thursday, the 4th of October, 1582, was followed by the first day of the Gregorian calendar, which was Friday, the 15th of October, 1582. But he made sure, they weren't stupid. They made sure that the day of the week just followed correctly. The reason was, if they went from Thursday to, let's say, what would it have been? Thursday would have been maybe Sunday or Monday the following week later, 10 days later, then people would have missed Mass on the Sunday, put their souls in peril. They would not have got paid for a week's work. They would not have had their day of rest. I mean, there would have been a revolution. So he said, forget it. We'll get rid of the days, but we'll keep the weekdays the same. So Thursday went to Friday, but the date went from 4 October to 15 October. And that fit. To understand that, this is the rule. This is the Gregorian leap year. So 1600, as I said, is divisible by 400, so it is a leap year. 1700, 1800 and 1900 are not leap years. But 2000 was. Okay. Yeah, Sydney leap year, it was a leap year. Well, let's have a look at it. Let's see how Clavius reasoned. Well, that meant in this 100 year, there would have been 24 leap years and 76 non-leap years. The same in the next and next, but on the fourth one, there's 25 and 75. Okay, reverts to the Julian one. Okay. So that means there's 97. So 24 plus 24 plus 25 is 97. 300 years of 366 days. And then there's 303 days of 365 days. So that gives you 146,097 days in 400 years. Okay. Well, the average length of the year is therefore that number divided by 400, which is 365.2425 days, which is 365 and 97 over 400. There's 97 over the 400. And it gives you that exact number, which, as we saw, was very, very close to the tropical year. So the difference between the Gregorian year and the tropical year is 26.78 seconds, which I think is pretty impressive. Okay. Now, there's 86,400 seconds in a day. So, if you divide that by the difference here, it means that in every 3,226.29 years, you'll lose 1 day. You'll be out by 1 day, which is pretty good. And for all intents and purposes, we're never going to see that. Okay.
Isn't that your seconds? 3,226.29?
No, that's how many, because remember, that's the difference in the year.
Yeah,
so you divide that in there.
You're not following.
Yeah.
We're losing a second every year. Anyhow.
No. Why?
We lost a second last year,
No, I'll come to that. No, it's not quite the same. Not the same. Not the same. I thought someone might get it, it's not. So in other words, instead of losing one day every 4 years, you lose one day every 3,226 and a bit years, which is pretty good. I think you'll agree. So Clavius was pretty good. Compare that to the Julian leap years. Well, you got the same across there. You'll end up, there's the number of days there, so you end up with that number of days, which is what you expect. There, which is 100 over 400. So the difference then is the difference between the Julian day and the tropical Julian year, the tropical year, is 674.78 seconds, which means that you lose one day every 128 years like that. Can you follow? So that's why. So now the Gregorian year, so in 400 years, the Gregorian year you will lose 2 hours, 58 minutes and 32 seconds. In the Julian calendar you lose 3 days, which is pretty good. I'd rather lose almost 3 hours than 3 days. Okay. And so the calendar was adopted in 1582 by all the Catholic countries of Europe. Because remember, this was after the Reformation, so not all the countries had allegiance to the Pope. And so it was those countries. And then over the years, more and more countries joined. In 1752, Great Britain and its colonies finally switched. 1752 followed here. And the last country to switch to the Gregorian Christian calendar was, amazingly, Saudi Arabia in 2016. Okay, they finally had to adopt it because they need to if they want to do business. Okay, and the interesting thing here with Great Britain, one little side note, is that Isaac Newton has been known to have been born on Christmas Day, 1642. But in those years, okay, Britain was still using the Julian calendar. So in the Gregorian calendar, he was actually born on the 5th of January. Okay, and it wasn't until about 10 years later that they switched. But his records always said, his birth certificate at his baptism said he was born on Christmas Day, 1642. Yeah, interesting side note. And I thought Clavius was pretty good. But another really brilliant astronomer and mathematician in the early 20th century came along, and this guy is another enormous brain. It was Milutin Milankovitch. He's now famous as being the originator of the Milankovitch cycles, of the orbits of the planets and tilt of the Earth and so on. And he came up with, he's a Serbian astronomer and mathematician, and he devised a new calendar which was more accurate even than the Gregorian calendar, as you'd expect, being in the 20th century. Okay. And it was that calendar which was adopted by the Eastern Orthodox churches because for their ecclesiastical purposes and so on. And so, and that in 1923. So in the revised Julian calendar, as it's called, it has the same months and month lengths as the Julian calendar, but in that revised calendar, years evenly divisible by 100 are not leap years, except that the years with remainders of 200 or 600 when divided by 900, and so on. So in other words, yeah, and so what does that mean? Well, it means that in 900 Julian years, there are 225 leap days. And so the revised calendar admits 7 of 9 century leap years, leaving 218 leap days per 900-year cycle. Thus, the calendar mean year is 365 plus, actually that's not a plus, 365 and 218 over 900 days. But this is actually a double cycle that reduces to that days, or exactly that immense. So in other words, this is 365.242, which is even closer to the tropical year than the Gregorian calendar. So in the long-term average, the revised Julian calendar pulls ahead of the Gregorian calendar by 1 day in 3,600 years. Which again, for all intents and purposes, for us now, is forget it. Makes no difference to us. Okay? So is that clear? Why we have the leap years and how we got there, and so on. And now to David's question. The leap seconds. Well, that's a modern thing, because up until recently, we couldn't measure the day all that accurately. In fact, the second was defined as a fraction of the year 1900 up until a few years ago. Okay. It's since been defined as a certain number of oscillations of a cesium atom. But nonetheless, we can measure the year to very precisely nowadays. And the reason why we need to is because the moon raises tides on the Earth twice a day. And this results in the shortening of the days. Okay. Here's the Earth, there's the moon, not the scale. The moon's further away. This part of the Earth is closer to the moon, so it exerts a greater gravitational pull. So that part of the Earth gets pulled towards it, relative to the centre. The part that's on the far end, okay, is further than the moon than the near end, so it lags behind the centre of the Earth, so you end up with this little bulge. So as the Earth rotates once a day, you have a high tide, low tide, high tide, low tide, and back to high tide. So you have 2 high tides and 2 low tides every day. And it's not just the oceans that do it, it's the ground that goes up and down too. Actually, the ground goes up and down every day by about this much. 40 centimetres. But we never notice it because everything moves up and down with us. Okay. And so, but you still have to take all that into account. The other thing too, this diagram shows the Earth to be a brilliant, smooth billiard ball. We know that's not the case. There are mountains and oceans and continents in the way. And so it doesn't just point towards the moon and then it just moves underneath it unrestricted. Instead, the friction, the oceans with the Earth, cause that bulge to move forward a little bit ahead of the Earth-Moon direction. Can you follow? And what that does, because there's more mass slightly ahead, that tends to pull on the moon, drag it around, like on a string, which speeds it up. And in an orbit, when you speed something up, you actually push it further away. Okay? But while it's doing that, the moon is dragging on the Earth, slowing it down. So you have a conservation of angular momentum. So as the moon goes further, gets thrown out further, the Earth slows down by the same amount of angular momentum. Okay? And so we can actually measure the drift of the moon because Neil Armstrong and Dave Scott on Apollos 11 and 15 put laser retroreflectors on the moon. We can fire lasers at those reflectors and time the travel time of the pulses, the light travel time, and determine the distance to the moon, and they've been measured to be moving out by around 3 or so centimetres a year, moving further away. But that has the converse effect of slowing the Earth by 0.002 seconds a day. That is 2 milliseconds a day. So every day is 2 milliseconds slower than the previous day. Okay? Can you follow? Now, in other words, the inverse of that, you get 500. So in other words, it takes 500 days for the Earth, for the day to slow down by 1 second. Okay? Now, if we didn't correct for it, then everything starts drifting off again, just like the Julian calendar. So we have to add an extra 1 second every 500 days, or about every 1.5 years, to keep the day in sync with the accepted civil time. We don't want to have to continually adjust our clocks, then we have to adjust it. Okay? So leap seconds are usually inserted on the 1st of July or the 1st of December every 1.5 years. Can you follow? Okay. So in other words, we do that by just stopping the clocks for 1 second and then starting them again. And so we had one a few recently. I think we're due for another one soon. But on the 1st of July 2015, we have atomic clocks here on the observatory. They're some of the most accurate clocks in the world, so they're used as the time standard for the Earth. But on the 1st of July 2015, we had to insert a leap second, and so we videoed the clocks upstairs to see what they would do, and they each did something different. Here we go. Time now. You can see it stopped for at 10:01. Well, let's look at Australian. At 10:01, it stopped for 2 seconds before resuming. So I'll do that again. And again. However, if you look at the other clock, this one, it stopped at 10:59 and 59 seconds for 2 seconds before resuming. And I know we didn't have it here, it was off on the other. On one of the other clocks, it actually went to 10:59 and 60 seconds and then went to 0. So that was weird. Never seen that before. So you have to insert that leap second to keep the Earth's rotation in line. And the reason we have to do all that is because that's the time we all live by. We want the seasons to occur at the same time every year, roughly, so that we can make plans. We want the time to be consistent, so we're not late to meetings by 1 second or so. And all these other things. And over centuries, it makes a big difference. Okay? So if we want to keep civil time, that's how we do it. And the story of how we got our calendar taken millennia to get here. But the whole world has now agreed on it. And it's pretty consistent now. And with that, we can do a lot of really nice things about it. Okay? So with that, I'll finish there with claiming this at the top. Thank you. That wasn't too complicated, was it? It's very simple math. It's just addition and subtraction and division.
John, could you just go back and explain a bit about the leap years again?
But the point is, now remember the early calendars were all lunar. Okay? Because you didn't have to do anything to know what, to figure the time. You just look up and see the moon. So if you're a nomadic people, okay, that was brilliant. Because you just look up, oh yeah. So if you're wandering around the desert, as the Hebrews did, or the Arabs did in the Arabian desert, it made sense to have a lunar calendar. Okay? But to have a solar calendar, you actually have to make measurements to determine the length of that year. Right? How would you do that? I can look at the moon and say, look what phase it is, but not too many people stare at the sun to determine where it is on the sky. Right? But what do they normally do? No. You would look to see where it rises or sets. Okay. And you would notice that as throughout the year, it will move north, stop, and come back, go south, and go like that. Okay. Now, so you might plot the position so you might go outside your home one day, stand at the same spot, look past that post over there, and relative to that post, you can say, okay, the sun's rising over there, and then it starts moving up, goes all the way, and comes back. And 365 days later, it's back where it was. Oops, the year is 365 days long. Okay. Except when you then look at it the next year, was it quite there? No. But 4 years later, from the beginning, when you're it's a day, it occurs a day before. A day after you expect it. Hang on. So another 4 years, it's 2 days before. And then another 4 years, it's 3. And so you very quickly realize, oh, hang on. It's not 365 days, it's 365 in a quarter days. So every 4 years you'll lose that 1 day. And so it's 365 days. But what is that? How do you get that? You get it because you're in one place. Okay? You're not out wandering in the desert in the bush, where every day you're looking somewhere else. Okay? You have to be in the one place so that you can check it every day, at least for a year. And then if you want to get it exact, at least multiples of 4 years. Okay? So in other words, you have to be settled. So it was only when mankind became civilized and got settled that they could then do those measurements and determine what the length of the year was. Which is why the Sumerians, the Babylonians and the Egyptians were the first to do it. Because they needed to know, because they needed to know when the seasons were going to occur, because they were growing crops. They weren't out, nomads wandering from one paddock to another with their livestock. They had to know that, so they needed to know that. So it meant solar calendars developed when men became settled and began agriculture and so on. Okay. So that's why the solar calendar began. And why with the Hebrews, who were nomadic people, they didn't want to carry along big things. It's easy just to look up at the sky. The same with the Arabs in the desert and so on. Okay. And so only when people became settled could they then switch to the solar calendar, because they needed to know that. It was vital for them. Can you follow? And nowadays, of course, we need to know, because we're sending things to Mars and the Moon. If we're 1 second out, the difference between landing and crashing and so on. So you really need to know these times very, very precisely. And our GPS, you not only have to know times to nanoseconds, we need to take general relativity into account also to make it work. So. Yes.
Wouldn't it make sense to treat the discrepancy in the same way that we do for leap seconds? You just take the difference between the tropic year and 0.25, work out how many seconds that is, and insert it every day.
Yeah. Well, the problem is you can't get everyone to agree. The Pope could get away with it in the past. Because he said, "That's it, finished." Who's going to order that on everyone? Because there's too many vested interests. There are astronomers, and remember the second was really defined as the fraction of the year of a year. Okay. If you change that, you change the length of the year, then all your frequencies will change. Everything changes. The frequency of the hydrogen atom will be different once you do, because it's no longer 1420 megahertz. It's something else. Slightly different. But you know what I mean? The constants of nature will change. So you don't want to change it. You want to keep it fixed. Okay, which is why they switched back in the 60s to the number of oscillations of the cesium atom. I've forgotten which isotope, but so that's constant, so that you can keep it. And then there are businesses. They don't want to keep adding it, because imagine we have enough trouble with daylight savings, for God's sake. Okay? You imagine sticking in another second every few years, and then after forget it. The scheduling things becomes horrendous. There are all sorts of problems, and no one can agree. So in the end, astronomers just take it. They don't even do that. Astronomers use what's called the Julian date, which is not related to Julius Caesar, but to a mathematician called Julius. What's his name? Julius Springer or something. He went back in time to like 4,000 and something BC, before any civilization existed. Okay, I'm going to call that the year zero, and we'll measure everything from there for all of history. So astronomers just keep adding the next day. They don't worry about a calendar. They just say, what year is this? Well, this is the year 5,882 on the modified Julian date. And then tomorrow will be 5,883 and so on. They don't have a calendar. So as long as you can keep the time constantly fine.
John, how long have astronomers been using this? Oh, sorry. Keep that.
Got a question from Rick.
Rick?
Oh, Rick.
No.
Come on, Rick. It's a complicated question to understand.
Okay. I should have that, yeah. You recording that?
Just don't have to.
I just thought you were.
So I truly don't understand one bit, but not so bad I can't try and clarify. The leap second was after 500 days, adding up to 1 second discrepancy in the length of the day, not the time.
That's right.
The adding the leap second adjusts the time, didn't adjust the length of the day.
No.
So there's actually 500 days later, there's 1 more second in the day.
No. Because we simply say that there is 86,400 seconds in the day. And it's that keep it going. So by introducing it, you still,
So each second is slightly shorter. One way or the other. Figure it out, everybody. It's a second short. How many pulses?
so remember, this is only for the civil purposes. So we just introduced so that it's still 86,000. In other words, there's 86,400 seconds in the day. So 60 times 60 times 24.
So you need slightly different springs in the watch for same speed, which you don't notice. The hands go around.
So yeah, the day certainly is slower, but we still only divide it by 86,400.
So how long? So
For civil purposes.
Alex, I can wait up to your question. I've got another one.
So I can't hear you, sorry.
I'll wait for your question.
Oh, right. My question was just going to be, for Julia Day, how long is that system being used by astronomers? Was it used in Herschel's day, for example?
Yeah, I think it was 1700 something, wasn't it? I'll have to look it up. I meant to include it in there, but I thought I had enough in there already. So.
It's also the basis of computer time.
Julian day, yeah. So, like computers, if you're, well, one interesting, some operators, their start that time is the 1st of January 1970. You look at they all default to that, unless you change it. Because that's when the computers really came into their own.
No, Rick. No, I don't watch it. Oh, you don't want to overcome. Oh, sorry.
John, you mentioned the revised Julian calendar.
Blankovich,
Yeah, which is, as you said, is more accurate. But we're still using the ordinary Julian, aren't we?
yeah. See, all these countries, they still use. Everyone uses the Gregorian calendar, but for ecclesiastical purposes, the Eastern Orthodox, like in Greece, Serbia, and Bulgaria, and Romania, use the revised Julian calendar. In Armenia, like the Armenian calendar is based on the Julian. Okay, and so that's the ecclesiastical calendar. The Russians use the Julian calendar. So, for example, if they still celebrate. Everyone celebrates Christmas on the 25th of December. But for Russia, it's on the 25th of December. Okay, on the Julian calendar, but in the Gregorian calendar, it's the 7th of January. And in 2100, what's that? 80 years from now, it'll be on the 8th of January. But it's still the 25th of December in the Julian calendar. Okay, so there's an ecclesiastical calendar that the church uses to debut, to decide when they're having their feast ceremony. But for civic purposes, everyone uses the Gregorian, even the Arabs. That's the most amazing one. Saudi Arabia, even they adopted it. But because of that, a lot of these people, they don't like to use AD and BC. So they would use CE for the Common Era, or BCE for before the Common Era. But I use AD because it's easy to do that, and BC makes sense because what are we dating it from? Not from the founding of Rome.
Years ago, John, when I was in Thailand, I brought home a calendar because it was something like 2,500.
Oh yeah, I mean every culture has its own calendar. I mean I only mentioned the Hebrew one because that was what was used to determine Easter, which was the motivation for reforming. But there's lots and lots of it. Even the Roman calendar, I just gave a really dumbed down version of it. I said you need multiple PhDs to follow the Roman calendar because it was so corrupted. The emperors and consuls would just change it at will. People had no idea what day of the year it was most of the time in the Roman calendar until Julius Caesar fixed it. But even then, they still mucked around with it. Like Julius Caesar, he stuck his own, renamed one month after himself, and Augustus put another one. Other emperors tried to do the others, but people got sick and said, forget it. So it stopped. So we ended up with July and August, but that's it. So it got really corrupted. And so the trick is don't muck around with it. Keep it so that everyone is consistent.
Any more questions?
As I said, the whole problem is that the number of times the Earth spins on it is not a multiple of its period around the sun. And that changes, you know, because as Milankovitch showed, the orbit and everything, so it all changes. So you might as well just pick a thing and stick to it, which is what they've done.
Anyway, thanks, John. That was very, very interesting. I'm glad
I hope it wasn't too complicated, you know.
I'm glad I listened to it because I like to learn one thing every day. I got one thing out of that. I now know why earthworms are long and skinny. Anyway, we thank you very much for putting that talk together. And,
Years ahead of you.
sorry?
You've got 100 years ahead of you. Learning something new every day.
Oh, that's true. No, that's
36 hours.
So we'll adjourn and have our